So these are the axioms for addition. Now we do multiplication. Yes, this is going to be forever. I'm sorry. But I'm going to try to summarize these. So multiplication says for all x and y, x, y is an f. So they're the exact same thing, except for a couple of them change a little. For all xy equals yx is the commutative property of multiplication. M3, same thing as over there. Which one is it associative, right? X, y, z, in parentheses here, equals x, y, z. What am I missing? M3. So M4. So this is one of the ones that changes. There exists one in F, one not equal to 0, such that 1 times x equals x. Right? And I'll ask for questions in a second. I'm just getting tired writing on this. I didn't realize I'd take this on. So now this is where I'm going to change the beginning. For all x in F, x not equal to 0, there exists 1 over x in F, such that 1 over x times x is the identity. I still need one more rule. Curses. And this is the distributed form. So again, for all x, y, z, and f, x times y plus z is equal to xy plus xz. If I didn't put the dot, it's still there. It's just, you guys understand that. Right, so there's all these horrible rules that we basically learned about the real numbers and the irrational numbers and all this other stuff. I don't know. When do you learn these? Like, I don't know, 6th grade or something? I don't know. But does this make sense? So basically this says I can add, subtract, multiply, and divide exactly as you expect. If you're in it. So the only place you can add, subtract, multiply, and divide exactly as you expect. Does that make sense? And that's the field. So I know that was a lot of writing, but let's just, let's take a second and think of some examples. Can you guys think of an easy example of a field? It was a field. This is probably, in fact, as far as you guys are concerned, the most basic field that you can come up with. Let's see if we can come up with another one. Anybody else? Let's just pretend, actually, let's not worry about it. Let me ask you this. Is the empty set a field? I heard a couple no's, I heard a bit of grumbling. So, honestly, is the empty set a field? No. Why not? It doesn't have an identity. This is something I tell every time I teach something with actually I define the field like I think every semester in summer for years now. This is one of the most important rules of being a field because it says this. So the reason you can't see it here is this says for all x there exists. So if the empty set doesn't violate any rule but this one and M4. Because this is telling me there is something in it. No. There does not exist a 0 in F. Okay, similarly, same basic, is the set with just 0 a field? Why not? There's no 1, because the other big deal is that 1 must also, in fact, the definition is specifically crafted so this is not a field. Because if this was a field, every single theorem in linear algebra would say vector space over a field that's not 0. Okay. But no, this is also true. There does not exist 1 in F, 1 not equal to 0. Because the thing is, this does have a multiplicative identity. I don't know if you noticed. 0 times 0 is 0. It is its own multiplicative identity. But it's not a field. Okay? Yeah. In which one? What is the reason for 1 not being a theorem? 1 not being a theorem. Oh, the reason is specifically because you don't want this to be a field. Like, I'm being serious. It's literally to exclude that one example. That's why I put it up there. And the reason is, every time you use fields, you really don't want one to be equal to 0 because the zero field is just a nightmare. It just nukes everybody. It's zero world field would be a nightmare.
Yeah. How can 1 equal to 0?
Well, so here's the big deal. When I'm saying that there's a 1 in x in this thing, I mean there's a multiplicative identity. There's something that when multiplied by anything else in the set, it gives you back the set. Think about this. What's 0 times 0? 0. It is this multiplicative identity of this set, if you give it the standard multiplication. See what I mean? 0 is acting like the identity of the multiplicative identity and the additive identity. But it's equal, these two can't be equal. That is literally what we mean. So this is an algebraic idea. If you took 113, or when you take 113, you'll see this a little more, because you define this for some types of rings. But the thing is, there's an idea of just places you can add in. So fields are nice, because you can add, multiply, subtract, and divide. You sometimes don't care about division, so you ignore division, and things can get worse. And this is still an arithmetic. Like you can still add, subtract, and multiply in this thing. And it still sort of works, but it's just a nightmare. Does that make sense?
So in that case, 0 is acting as
both 0 and 1. See, in fact, to say that there does not exist, it's really the problem is 1 is equal to 0 is really the problem, if I were to really summarize it. Because the additive identity is 0, because 0 plus 0 is 0. And the multiplicative identity is 0, because 0 times 0 is 0.
Okay.
See, and so what it's actually violating is this part. It's not actually violating the existence. This one was violating existence. This one was not. This was just violating that they weren't equal. And literally, in I didn't catch your name. Will, as Will pointed out, like this, the only reason we add this line is to exclude this example. Period. Great. So I had one other example. This is just. So what about if I give you the set 0, 1 with binary addition? Well, by that I literally mean 1 plus 1 equals 0, and otherwise everybody else multiplies how you expect. Is this a field? Turns out this is a field. I just wanted to point this out, just so you know that Q and R and C, which we're going to talk about in this class, this we're not going to talk about much more beyond today, are fields. There are other fields. There's actually an infinite number of fields. In fact, for every prime number, there exists a field that has exactly that many elements. And in fact, for every prime number, there exists a field that has exactly p to the n for any n elements. And there's a lot of these things. And they live all over the place. And if you want to learn about them, take 130. Not in my class. But okay, the point is, there's a lot of fields. I just wanted to point out they're important only because R is a field, C is a field, and after that I don't really care. So we're not going to go into the details about this, but we're going to actually talk about specific kinds of fields today. I need to go find out where I'm going with this. Great. Okay, cool. So let me prove a simple proposition now. Let's just get us going with easy proofs. And, I mean, I hate to say it. There are very few easy proofs on the homework. I think number 1 is really easy. I don't remember though. So I'm going to prove a proposition. So this is right from Rudin, but I'm just going to go through maybe a few of the parts of the proof. This isn't exactly from Rudin. So if F, if F is a field X, Y, and Z and F, then the following things are true. If X plus Y equals X plus Z, then Y equals Z. Oh, I forgot how much I did this, but no, I was going to make a point. I was going to tell a bad joke too. There we go. Bad jokes make everything okay. Then Y equals 0. C, if X plus Y equals 0, then Y equals the inverse. Minus X, I just realized a mistake in my notes, equals X. That's all I'm going to put. So let me explain what I mean by these. So these kind of are self-explanatory. What I mean here is the additive inverse of the additive inverse of X is X. Okay?